I want to show you a proof of the generalized theorem of calculus. Let's consider a k-1 form defined on a k-dimensional manifold. We define the form to be alpha. This form can be written in the following fashion: 1 over k-1 factorial alpha I1 I2 I k-1 because it's a k-1 form. Then we have dxi1 wedge wedge dxi k-1. And notice that since the manifold is k-dimensional, these indices I1, ik-1, they go from 1 to k because it's k-dimensional. Now this form can be expanded, and by expanded I mean that we can sum over the indices I1, I2, ik-1, and therefore we can write it in the following fashion. In particular, we can write alpha in the following way. So I'm going to write as alpha j, and then I will explain more in detail. But first let me write alpha j, which is a function of x1, xk, just like this. And then I have dx1. Pay attention because here I have the index 1. It's not I1. Then I have wedge dx2 wedge ... Then I have dx hat. I will explain in a moment. First let me write it, dx hat j. So here first I have a wedge, then I have another wedge, so wedge dxk. Now, first let me tell you that this hat means or indicates that dxj is missing from this differential. So in particular, what this means is that, so another way to write it is simply by writing like this: dx1 wedge dx2 wedge wedge dxj minus 1. Then I have wedge dxj plus 1 wedge wedge dxk. So it means simply that dxj does not appear in these differentials. So why is that? Well, it is not so difficult to understand actually, because since this is a k-1 form, we need to have k-1 differentials. So if we start from the index of 1 and we'll go all the way up to k, then k differentials would appear. But this is not possible because this is a k-1 form. So we need to have k-1 differentials. So the differentials that will appear, for example, are of the following form. We can start from dx2 wedge and we go all the way up to dxk. So these are k-1. But of course you can also have dx1 wedge dx3 wedge dx4 wedge wedge dxk. So in this case dx2 does not appear, and so on. So you can remove one differential, and then of course you can make up your series of differentials, your composition of differentials. Hopefully I'm making myself more clear now. And since we are summing over j, so here we are summing over j, you can see that for a different value of j, there is a different missing differential. So we are taking into account the possibility that we can have all such combinations. Now, hopefully this is more clear now. At this point, I can also take the exterior derivative of alpha, and the exterior derivative can be written in this form. So I have d alpha j dxi wedge dx1 wedge wedge dx hat j. Now we know how to interpret this, wedge dxk. Now, at this point, you can realize that since we are in a k-dimensional manifold, the only possibility for the index I here is to take the value j. Why is that? Well, it's easy to realize because if we take, for example, I equal to k, then we have dxk here and dxk here, and therefore this composition of wedge products will give us 0. So the only non-zero contribution is when I is equal to j. And therefore, we can also write it in the following fashion. So we sum over j. Now I'm highlighting the fact that we need to sum over j because in this case we have j appearing 3 times in this expression. So I have d alpha j dxj. And since it appears 3 times, I want to remove the ambiguity because it's a little bit ambiguous and I want to stress the fact that we need to do sum over j. Usually when I don't write summations, when I don't indicate the fact that we need to sum over j, well, that kind of indication is implicit in the fact that there is one lower index and one upper index. But when we have 3 indices and the other index is here, it's not so clear what we need to do. So I'm going to stress it by putting the summation over j here. And then I have dxj wedge dx1 wedge dot 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 wedge. We have dx hat j, so this is just a formal expression, a formal way of saying that dxj does not appear here. It appears here. Then I have wedge dot 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 wedge dxk, like this. So at this point, I can also rewrite it in another way. In particular, I can put this dxj in this position. If I swap the order between this, and then I swap the order between this and the next one, and then I swap the order with this, and the next one, and so on, until this differential goes to this position. And I can do that, but I have to take into account the fact that some factors of -1 will appear. And how many factors will appear? Well, I need to do j-1 swaps. In particular, this means that I need to move dxj to the right by j-1 positions. So I have the summation over j, and then I have a factor of -1 to the power j-1, because I have j-1 swaps. And then I have d alpha j dxj dx1 wedge dot 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 wedge dxj. So at this point I don't have this hat anymore because dxj appears in this position. And then I have wedge dot 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 wedge dxk. And it will be more convenient now to rewrite this as the differential dkx. So this is just a definition for now. It will help us save some ink without needing to write the entire expression. So this also means that we have to sum over j -1 to the power j-1 d alpha j dxj dkx, like this. The next step is to rewrite this function here alpha j by using a well-known theorem of analysis, in particular a theorem that tells us, or that states, that a smooth function alpha j, and remember that alpha j depends on x1, x2, dot 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 xk, since we are considering a k-dimensional manifold and a k-1 form. If we have a function like this, which is smooth, and it is defined on a closed and bounded region of Rk, then it can be uniformly approximated by linear combinations of products of smooth functions of one variable. So this seems like a complicated sentence, a complicated expression, but it simply means that basically we can write the function as a product over q, a variable q, from 1 to k, of functions of this kind that we will label b, qj, and it depends on xq. So this is basically a product of the following kind. We have bj1 of x1, bj2 of x2, dot dot dot, bjk of xk. And it is a linear combination. So in general, we can also take summations of functions of this form, but due to the linearity of integrals, we can simply assume that this function can be written like this. And the next step is to use this expression when we integrate the alpha. In particular, we integrate over some manifold, some k-dimensional manifold, and we will assume that this manifold is a k-dimensional cube. So it's a hypercube in k dimensions. We will indicate the hypercube like this, I to the power k. This basically means that we have an interval, so this I stands for an interval, for example, an interval from A to B, and then we raise to the power k, so we get basically some cube. If we want, for the sake of convenience, consider a unit k-dimensional cube, so a cube whose sides are all equal to 1, we can also consider each interval I from 0 to 1. We can define it like this, and then we have ik that defines the space described by the cube, spanned by the cube. So this is what we want to calculate. We will show that this will be equal to the integral over the boundary of the cube, that we can indicate like this, and then here we have the k-1 form alpha. So we continue our proof of the generalized fundamental theorem of calculus. We know that we have to integrate this k-1 dimensional form, in particular the exterior derivative of the k-1 dimensional form that we called alpha. We have to integrate it over this unit k-dimensional cube. So let's do it. We have an integral over ik, then we have a summation over j. I'm simply replacing the expression for the alpha. Remember that we have this factor minus 1 to the power j minus 1, derivative alpha j with respect to xj, and then I have dkx. So remember also that we define this dkx, it's an object that encloses the following differentials, dx1, wedge dx2, wedge dot dot dot, wedge dxk, like this. Now, at this point, I can also use a theorem that we used in the previous lecture. In particular, we want to use this formula, basically. So we can approximate such a function with a product of functions of only one variable. And basically, this is an integral, I to the power k, summation over j, minus 1 to the power j minus 1. Then we have this derivative with respect to xj, and then I have a product over q from 1 to k, b q j x q dkx. I have simply replaced this expression here. At this point, I can also write it as integral over I to the power k, summation over j, minus 1 to the power j minus 1. Then I have b1j x1 dot dot dot. I have the derivative, which is only going to act on bjj of xj, because it's only bjj that depends on the variable xj. Remember here that we are just considering a derivative with respect to xj, so the derivative is only going to act on bjj there, and then dot 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 bkj xk dkx, like this. At this point, I'm going to rewrite it, in particular this integral here. I'm going to rewrite it in the following fashion. So we have summation over j, which is here. Then I have an integral over the variable x1. I have an integral over the variable x2, dot dot dot. And then I have an integral over the variable xj, but here I'm going to put this hat to denote the fact that this integral does not appear in this position, but all the others will appear. So I have an integral over xk. So this is just some notation that I will clarify in a moment. So why am I choosing this integral here? Why am I choosing to to remove an integral over xj, because I mean the answer is simple. It will appear somewhere inside the somewhere here, but I will show you in a moment. Then I have to remember adding, I mean considering this minus 1 to the power j minus 1. I have b1j x1 dot 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 bj j minus 1 x j minus 1. Then I have bj j plus 1. So I'm not considering this term because I'm going to consider it after after this expression that I'm writing now. So I have bj j plus 1 of x j plus 1 dot dot dot. Then let me continue here. I have bjk of xk, and then at this point I'm going to write it. I'm going to write the integral over xj here because it's missing here. Therefore, I need to write it somewhere, and I'm going to write it here. I have integral over xj over the variable xj dbjj of xj dxj dxj. So if I put the differential of xj here, I have to be careful because remember that I have the expression dkx, and dkx contains dx1 wedge dot 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 wedge dxj in general, but since I have put dxj here, I'm going to put a hat to remind myself the fact that this is missing because I'm considering dxj in here, right? And then I have wedge dot 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 wedge dxk like this, and now since I have put dxj here, I have to be careful because it means that I have moved the differential from here to here. So I have moved it to the left by j minus 1 positions. So I need to multiply this by minus 1 to the power j minus 1. So I get another factor like this. And if you want to be more precise, here you can also put a wedge if you want to be more precise, because at the end of the day, here I have a differential, and then I have to take the wedge with all the other differentials. So for the sake of convenience, I'm not going to write this wedge. I'm going to write it like this, and I'm simply considering this integral. I will perform the integral now, so I can do it in the next line. Summation over j, integral over x1, dot dot dot, integral over x hat j, so it means that this integral does not appear, integral over xk, b1j of x1, dot dot dot, b hat jj of xj, so it means that this quantity is missing from what we are writing here, but all the others appear. And then I have bjk of xk, and then I have to multiply this by bjj of 1 minus bjj of 0. So basically I have integrated over the variable xj, and I have to integrate it from 0 to 1, because remember that we are integrating over a k-dimensional cube, so we are integrating from 0 to 1. When I write the integral over xj, this simply means that I'm going to integrate from 0 to 1 over the variable xj. Simple as that. So in this case, of course, when I write it like this, after performing the integration, it doesn't make sense if we put a wedge product here. So that's why I have not put the wedge here, because after we perform the integral, this integral here, it does not make any sense if we include a wedge here, because here we just have some numbers, and therefore it is convenient to avoid writing the wedge here, and therefore we don't have the wedge here. So I know that this sounds a little bit informal, but it is actually how we define the integration when we do integration, when we perform integrations over differential forms. And then I will be left with dx1 wedge dot 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 wedge dxj hat, so this will not appear, wedge dot 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 wedge dxk, like this. And at this point, I can rewrite it one last time, so I can use the fact that we derived this expression. I can put bjj here, and then I will have minus this same thing, where instead of b hat jjxj, I will have bjj of 0. So let me show you if this is unclear. So I have to sum over j, integral over x1, dot dot dot, integral over x hat j, so this integration does not appear, dot dot dot, integral xk, and then I have bj1 of x1 dot 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 bjj. In this case I have 1 here because I have integrated over the variable xj, dot 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 bjk of xk, and then I have plus, let me put a minus in here, b1j, so bj1 of x1 dot 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 bjj of 0 dot 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 bjk of xk dx1 wedge dot 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 wedge dx hat j wedge dot 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 wedge dxk, like this. Now you can notice the fact that this is simply equal to alpha j of x1 dot 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 xk evaluated at xj equal to 1, whereas this is simply equal to alpha j of x1 dot 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 xk evaluated at xj equal to 0. Simple as that. And now, with some intuition, it is quite easy to see that this is exactly coincident with an integral over the boundary of the cube of alpha, so of the differential form alpha, because you can see that we have alpha j multiplied by these differentials, but when we consider j multiplied by those differentials, and in particular also when we consider the summation over j, so this summation can be put here if you want, but if you consider that, basically we get our differential form alpha written like this, which is coincident with this notation if you want. So they are just two different notations, but they are completely equivalent. And therefore, if you try to think about it, if we consider the differential form evaluated at xj equal to 1, and then subtract the differential form evaluated at xj equal to 0, we are simply considering the integral over the boundary, because we are integrating over a boundary now. Now, at this point, this derivation seems a special case, because we have chosen to integrate over a cube. But let me tell you that a generic volume in general can be decomposed into quote-unquote small cubes, and the non-zero contribution will be given by the faces of the cubes which lie on the boundary of the manifold. In particular, the contribution over faces of adjacent cubes will cancel out. It is simple to see this in 3 dimensions, because if we consider, for example, a small cube like this, and then we consider an adjacent cube in here. Now this is just a sketch, a simple sketch, and then we consider this face in red. Then we have to consider the fact that these faces are oriented. So for one cube, the normal to this surface will be in this direction. In particular for this cube here, if we choose the outward pointing unit normal, this will be oriented like this. But then for this other cube, the normal will be oriented like this. And therefore, when we add all the contributions, the net effect of such a contribution here will be zero. So zero contribution. And that's why I said earlier that the non-zero contributions will be given only by the faces of the cubes which lie on the boundary of the manifold.